All right. Okay, so we had a bunch of little projects going on, and I'm gonna be working on some stuff, and I think maybe my friend Kevin might be also instead of the DDS VFO, we're gonna be ordering a synthesizer, Arduino, the cheapest one possible, a display, an encoder, and some other stuff to experiment with these in certain older CB radios. The main thing is that we need the software or the sketch or whatever you call it that will tell this thing to display channels 1 through 40. I'm not concerned with extra channels or any of that. Like, it's a CB radio. I want it to work on channels 1 through 40. If I want to work somewhere outside of that band, I use a ham radio. I don't operate illegally. I don't do stuff I'm not supposed to do. So, at any rate, I don't need to be out of the band. Okay? We got, as ham operators or even as CB operators, we got more than enough stuff to keep us busy. There is plenty of stuff out there. You don't need to be operating in illegal parts of the bands. There's plenty to do. So, right now I'm looking at. Hold on. Right now I'm looking at this guy here. They're bring your projects to life with Arduino software, and so basically, there's a couple of things that I'm gonna have to learn how to do, which they call it Arduino IDE, which is let's see, we'll back out of it. It is this tutorial will walk you through downloading, installing, and testing the Arduino software, also known as the Arduino IDE, short for Integrated Development Environment. So before you jump to the page for your operating system, make sure you've got all the right equipment. So anyway, a nice little write up here on Spark Fun Electronics. Required materials, you'll need the following materials: computer, Windows, Mac, or Linux. An Arduino compatible microcontroller, USB to A to B, blah blah. Anyway, Arduino R3, is that what we want to use? I don't know. Those might be a little bit easier to program and stuff like that. That I think is what they use in the printers, maybe. Anyway, there are a couple of things here. If you're new to Arduino in general, you want to check out this tutorial to familiarize yourself with everyone's favorite microcontroller platform. What is an Arduino? February 26th. What is this Arduino thing anyway? This tutorial dives into what Arduino is, and along with the projects and widgets. AT Mega 16U2 on the Arduino Uno R3. I've seen some of these boards and different knockoffs in some of the 3D printers, I'm pretty sure. Anyway, the how to install FTDI drivers, how to install CH340 drivers, some interesting stuff there. It definitely could get you tripped up, I'm sure. Download the IDE. So this is a page that we're gonna bookmark this, and we'll come back to it later. But let's see here. For now, let's go over to Circuit Secrets, CIR. Of course, my camera is in my way. So Circuit Secrets has the YouTube channel, and then they have a Wix website, which is not all that great. I've got a Wix website too. They're a pain in the butt. It's no fault of them, but anyway. Yeah, tube preamp that he advertises. Circuit Secrets PA layout. And then it goes through some other projects. And this doesn't show up very well on a mobile device, but encoders, Pico, Raspberry Pi, CB radio, VFO sketches, and we need that. We do. So we download that, and that sketch will allow us to compile the software on the Arduino. And instead of spending $100 on a Troy radio CB, we're going to be able to use Circuit Secrets sketch to try it out. Okay, so you might bookmark that website. There's not really any info on there, but you just bookmark it so you have it in case you need to go back to it. I'm going to go back into our search here, and we'll go to their YouTube channel. Okay. Arduino VFO installation. Well, there's a couple of a DIY VFO. This is kind of a video we will probably want to check out first. Let's move this over to the other screen really quick because I'm having a hard time seeing it over there. Okay. Let's get some sound here. We're going to mute the SDR play in the background.
Pro Mini. Welcome to Circuit Secrets. In today's video, I'm going to port the CB radio VFO code from the Raspberry Pi Pico to an Arduino Pro Mini. The CB radio VFO I created in this video works great. I have had it installed in my Cobra 21 for almost 5 months and it is still working perfectly. Someone recently gave me a CB with a faulty LED channel display, so I decided to try putting a VFO in it and replacing the display with the VFO's OLED. I checked the parts bin and found I was out of Raspberry Pi Picos. So, for the sake of using what I have, I decided to port the code for the VFO to another microcontroller.
Okay.
The microcontroller I decided to use is the Arduino Pro Mini. Since I have viewers from places with different standards for CB radio than we have here in the US, I decided this would be a great time to modify the new port to make it have roughly the same band range as the old export radios that used to be common. The frequency range of this VFO is 26.055 MHz to 28.305 MHz. After using my previous VFO, I decided that a new version would use an encoder instead of push buttons to change the frequency. If you make and use this VFO, please check the local laws and regulations to ensure you are not transmitting on a frequency or in a mode that is prohibited. To start, I created a build drawing as seen here. I used perf board and wired everything point to point just like the drawing.
Oh, cool.
Once it was assembled, I inspected it for short circuits, then tried running a couple of diagnostic sketches. First, I ran an I2C port scanner similar to the one in this video, but designed for one I2C port. The results were good, and the identifying addresses for the display and the SI5351 were both written to the serial port.
So we need an
Next, I tried an example sketch for
SI5351.
the SSD1306 display, then one for the SI5351. They each worked great. Then I tossed some code together to read the encoder and output the results to the serial port. This worked as well. So the next step with working hardware was to start porting the code. Porting the code from the Raspberry Pi Pico to the Arduino Pro Mini turned out to be quite a challenge.
I bet.
First, I developed the code to use both cores of the Pi Pico. I also used two I2C ports, giving the display and the SI5351 each their own data bus. This meant a lot of the code was split between setup, setup 1, loop, and loop 1. I moved all of the setup 1 code into setup, and I moved all of the loop 1 code into loop. Then I set both devices to use wire, removing a device from wire 1.
Pretty crazy.
After these changes, it seemed to run fine. The display worked, and the SI5351 output the appropriate frequency. But there were still a lot of changes to be made. The next step was to add the encoder.
So I wonder if you're better off to use the Pico.
The encoder at first without interrupts, just to see if it would work with the menu and channel selection controls. When I uploaded the sketch to the Arduino, the upload would go fine, but the Pro Mini would not display anything. After trying a lot of things and double-checking the hardware with the diagnostic method I used before, I found the problem. The sketch and libraries seemed to be too much for the Arduino Pro Mini, and a conflict was occurring. I'm not sure what the exact conflict was, but all I'm certain of is that when the sketch would take more than 80% of available space, the program would not run. So I stripped the menu system and simplified the code so all the options need to be set in the source code before upload to the board. This got everything working. Of course, the encoder was inconsistent because I was not using interrupts. I added the pin change interrupt to port C, masked it for pin 0 and 1, which are analog pin 0 and analog pin 1. Then I renamed the encoder function as the appropriate interrupt service routine. Once the encoder was working, I modified the code to display the frequency channel and set the VFO frequency. I added the ability to reach RC or radio control channels. I then changed the channel limits to allow access to the export bands. A few more tests and it seemed to be working as it should. You can find this VFO packaged
cool.
with the Pico VFO and a zip file on my website, circuitsecrets.com.
Okay, we already looked at
In the next video,
that.
I will attempt to install this VFO into a CB radio. If you enjoyed this content, please like, subscribe,
11,000 views.
Thanks for
2 years ago.
watching.
So, let's back out of here. So, let me go just see what all his videos are. I don't think he's been real active. A lot of people are that way, you know, they put out really good quality videos and they just only every once in a while, you know. They're not like me, they just put out crap. I just put out tons of crap. Programming with GPT. Okay, so I figured there would be a Raspberry Pi Pico. Yeah, I figured there would be. So, I don't know if there is a reason to use that instead. A Pico as the microcontroller. There's quite a few videos, so let's see what we got here. What is the ESP32? Huh. Let's see. Pico. Just trying to see if he's got any other interesting information. CB radio. Let's see. Okay. So, his oldest video is 5 years ago. It's a cool name for a channel, too. Circuit Secrets. Okay, so we've got the Arduino VFO, which is the one that we're going to need to worry about. But before I go ahead and start with one of them, I'm definitely going to want to check these. So it looks like there's 1, 2, 3 videos that I need to sit down and probably watch. And the reason that we're going to check his stuff is because there's nobody else doing this other than Troy Radio, and they aren't doing it for free. So
Welcome to Circuit Secrets. In today's video, we're going to be working with I2C displays on the Raspberry Pi Pico from the Arduino IDE. In the last video in this series, we covered the basics of I2C on the Raspberry Pi Pico by designing a port scanner. In this video, we're going to set up a display to emulate the display of a VFO for a CB radio. VFO stands for Variable Frequency Oscillator. Eventually, I'm going to be making a VFO that will convert a 6-channel radio into a 40-channel radio. The display we are using is a generic version of the SSD 1306. It is a 128 by 64 pixel display. Mine is on an odd address at 0x3C. Most of them are on the address of 0x3D. Now here we go into the code. The code begins by calling the wire library for I2C. Next, we call in the Adafruit library for the SSD 1306. Now we define the address for our display. If you are not sure of the address of your display, use the port scanner from my previous video. Next, we create an Adafruit SSD 1306 object as display 1. We then pass it the screen width, height, the port information of I2C, and the reset pin. We use -1 to indicate the reset pin is shared with the reset pin of the microcontroller. Next, we come to the variable we will use to indicate the current channel.
Well, I'm confused because it says Arduino.
I created the logo as a JPEG and converted it into hex on a website I will list below in the description. My logo is 64 pixels tall and 88 pixels wide. The bitmap must be converted to hex format to be used with the library and compiled in with the code. We designate it to be stored in program memory so it does not waste precious RAM space. Next, we come to setup, where we first set the pins to be used for I2C on the I2C port 1. Now we initialize the display object. We tell the display object to power on the built-in supply, and we pass into the display object the address of the display. This is in an if-not statement, which will begin an infinite loop if the display cannot start. This will prevent the code from advancing if there is a problem with the display or a connection. Next, we clear the buffer of the display and call our draw logo function. Then we delay for 3 seconds so the logo acts as a splash screen. Now we come to the loop. In the loop, we call the display channel and frequency function. Next, we increment the channel variable to emulate changing the channel. If the channel is greater than 40, it is returned to channel 1, like the channel selector on a normal CB radio. Next, we delay for a short duration before the loop repeats. Now we find the draw logo function. This function simply draws our logo on the screen. The first step is to clear the buffer with clear display. Now we tell the display to draw a bitmap. We tell it where we want the horizontal center of our graphic located, with the logo width divided by 2 subtracted from the display width. We repeat the same math for the vertical position with height. Then we tell it the name of the bitmap, followed by the horizontal and vertical size of the bitmap. Next, we output the buffer to the display. Next, we come to the display channel and frequency function. This function takes the channel number as an argument. Inside the function, we create a string to hold the frequency. Then we come to a switch that sets the frequency string to the appropriate frequency based on the
this a little bit.
RC channels are putting the channel in the text. Now we print. Again, we set the text 5x 2526.96 SI5351, showing our text. In the next video in this series, we will be working with the SI5351 on I2C bus to build an actual VFO. Thanks for watching. Please don't forget.
Alright. So we got to go back through here. Alright. So we got it. So I think that was the one we just looked at. Part 2, part 3. Where's part 1? Boy. Let's see here. Okay, so there's a video we're not seeing, but that's alright. Part 3. Oh, here's part 1.
Welcome to Circuit Secrets. In today's video, we're going to take another step towards a CB radio VFO.
This one's interesting because they're using a frequency counter.
In the past few videos on I2C, we have gotten the display in the SI5351 working. In this video, we're going to add inputs for channel selection and transmit. We're also going to incorporate multi-core programming for performance and add frequency offsets for mixing the VFO signal with other local oscillators. We are still using the same wiring as the signal generator, but now we have added 3 buttons for testing. In the final version, we will replace the transmit button with an optocoupler connected to the transmit switch of a radio. In its current state, the VFO has a standard offset of 10.240 MHz for mixing with a local oscillator on transmit, and additional 455 kHz offset on the receive. The channel selector buttons are working, but calibration and offsets are hard-coded into the sketch. Let's step through the code in its current state. First, we call in the libraries for the I2C, the display, and the clock generator. Next, we set the I2C add the offsets for oscillators from multiple times I2C. Block diagram showing all the setup is used. This spreads the load and allows us fast user input. The functions TX, we initialize the display. For the channel select, if it is true, we call TX for each to determine if we change the delay, and loop 1 is finished. Now we come to and move the button frequency, the information to the display.
So I think he's just going to talk all about the
frequency
code.
Yes, not hertz, offset frequency, CB radio VFO. If you enjoyed this,
okay, that was that one. All right. There's a bunch of these here. That's a part 3 to what? Here's part 1.
Welcome to Circuit Secrets. In today's video, we're going to take another step towards a CB.
Okay, that was part 1. Here's part 2.
Welcome to Circuit Secrets. In today's video, we're going to be working with I2C displays on the Raspberry Pi Pico from the Arduino IDE. In the last video in this series, we covered the basics of I2C on the Raspberry Pi Pico by designing a port scanner. In this video, we're going to set up a display VFO that will control pixel display. Next, we call in the AITRIP library for the SSD.
Okay. So there's a lot of information on his channel. Probably enough to where most of us could probably figure this out. These videos are just kind of hard to figure out what goes to what.
Welcome to Circuit Secrets. In today's video, I will be explaining and showing you the rest of the source code for the CB radio VFO. This is a continuation of my series where I show you how to build a CB radio VFO. This series started with an introduction to I2C and takes you through the basics of using an LED display, the SI5351 clock generator, and will eventually lead to the installation of the VFO in an old 6-channel CB radio. So please don't forget to like and subscribe. The source code is available at circuitsecrets.com. It's free of charge and no sign-up is required. In the last video, I showed you the source code and wiring diagram of the working VFO, but now it is improved with a menu that allows calibration of the SI5351 while in operation, and can save and load the calibration settings. The transmit and receive offsets are still hard-coded and must be set at compile time. This was done to avoid adding another switch to allow the large changes in frequency needed for adjusting those settings. Here's the wiring diagram. Now, into the code. First, I added the library for EEPROM emulation on PlayStation, which only stores data as byte, and typecast is self-explanatory. It is menu entry and code involved creating a menu system and a submenu for calibration. In the menu, I have 3 elements: calibrate, exit and save, and exit without saving. To operate the menu, I set up control routing from the button presses in loop 1. Menu entry and selection is accomplished by pushing both buttons at the same time. Most of this is done with switch statements. I chose switch statements because they are fairly easy to understand and perfect for the 3 states of buttons and 3-mode menu. I think that code is self-explanatory. It is similar to the other display text used in the video I2C Part 2 working with LED displays. The only other interesting change is in this section for calibration. Most of this section was lifted directly from the example code for the SI5351 from the EtherKit library. If you have any questions, leave a comment and let me know. The fully annotated source code is available for further study at circuitsecrets.com. In the next video, I will attempt to install the VFO.
Okay, so we've got. He installed this in more than one radio, though, and that's where I'm trying to find the other video. So if we look at, does he have a playlist, I wonder? Not really. Well, he kind of does. Okay, so probably this one.
9106 BP PLL chip. Welcome to Circuit Secrets. In today's video, I'm going to show you how to install an Arduino VFO in a Cobra 21.
Now you can see the display is a little bit crooked in there, but
this is intended for educational purposes only. It is illegal to transmit on certain frequencies in different places. Check your local and
you'll see it's a little crooked, but anyway, these things do fit in there pretty well.
Before attempting or using these modifications. Now let's get started installing the VFO I designed in this video into a Cobra 21. You can find the source code for the VFO on my website, circuitsecrets.com. The VFO is a variable frequency oscillator. This VFO uses the SI5351 for direct digital synthesis. So this is a DDS VFO. The radio I'm installing it in is the same as the Cobra 25 LTD Classic. It uses the TCP 91.
Which is what we just took parts off of
different years of production
the other day.
Chips, so confirm your radio has the same PLL before attempting this modification. The first step is to add a couple of components.
Which means I should probably put the parts back on one of them.
The radio operates on 13.8 volts. The VFO requires 3 to 5 volts, and any more would cause damage. I added the 5-volt regulator as shown in this diagram. I then added an optocoupler to protect the Arduino from any voltage present on the transmit switch of the radio. I wired the optocoupler to pin 13 as shown in this diagram. I performed this mod on this radio because the LED display had failed and it was a large enough radio to fit the VFO inside the case.
I don't know where I could get an optocoupler.
You can see places where extra components could be installed, but are missing here and here. I did not remove those components, but they were only populated at the factory for the Cobra 25 LTD Classic, and not the 21. This is because the Cobra 25 has more features such as RF gate.
I have a 25 and a 21.
I use this schematic because there is no schematic available for the 21 LTD Classic. Here you can see the PLL chip. This is the datasheet for the PLL chip. This shows the pinout of the chip. To understand the pinout, you need to know a little bit about PLL chips. They take a binary or binary coded decimal value.
I think the 21's that one they're pulling all the parts off of.
The channel selector is connected to these pins. As the channel selector changes value, the PLL receives different binary codes called encodes or numeric codes. The higher the value, the higher the frequency, unless it is inverted, such as is the case with some PLL chips. A PLL chip takes these encodes and outputs a signal to control a variable oscillator called a voltage-controlled oscillator, or VCO. The PLL also takes a signal from the reference oscillator. In a typical AM/CB radio, the reference oscillator runs at 10.240 MHz. The PLL uses this as a reference to measure feedback from the VCO to perform calculations to ensure it is on the correct frequency. The reference oscillator is also mixed with the VCO signal by the radio in the transmit and receive mixing circuits. This is the reference oscillator in the schematic. This is the VCO in the schematic. This is the transmit mixer chip, which performs direct mixing for the transmit carrier. This section is the receive circuit, which mixes down to the 455 kHz intermediate frequency indirectly in stages. These stages are sets of FETs and IF transformers calibrated with capacitors and adjusted to only pass part of the signal or an intermediate frequency. A frequency from the VCO that is 455 kHz lower than the output of the VCO used for transmit is needed for receive. This is why there are 2 offsets in the variable section of the VFO source code. The PLL chip reads the output of the VCO both to adjust the output of the VCO and to provide a transmit lock feature. The transmit lock is designed to prevent transmitting if the VCO is not functioning properly, to prevent transmitting on unknown or off-limits frequencies. On this chip, the transmit lock is labeled as LD or lock detect. In the datasheet, I find the LD is set low when the PLL is out of lock. Low logic state is considered ground. High state is whatever the PLL runs on. I believe in this case the PLL runs on 7 volts. With this information, on the schematic I can show you the plan to install the VFO. This is the VCO, so I will remove the transformer that is the last stage of its circuit before mixing. I will sever the PLL's connection to the VCO so it does not wildly change its voltage trying to lock, which could generate unwanted noise. I will sever the connection between the LD pin and the rest of the circuit. I will run a jumper from the PLL's supply voltage to the circuit normally controlled by the lock detector pin. First I will remove the channel selector and display.
Interesting.
Next, I cut away the mounting surface for the channel selector.
Yeah, you really do got to remove a lot of crap to get that thing to fit in there. And there really is no good way to do it.
To act as a display retainer for the OLED and the mounting point for the encoder. I cut a piece of an old mouse pad as a flexible backing pad to hold the OLED in place.
Okay, let's see.
Next, the board had to be modified to make it ready for the VFO. Many parts could have been removed, but I tried to keep the installation as simple as possible with the fewest modifications possible. I will start from the PLL chip where most of the modifications are made. This is the pinout from the datasheet of the TC9106 BP. First, I had to locate the output to the VCO and cut the trace. This is just a precaution to ensure the VCO does not seek and generate excess noise on the power buses. The oscillator out pin is labeled as XO. Next, I have to bypass the transmit lockout pin with the PLL and set the output to high. The transmit lockout pin is labeled LD for lock detector. I bypass it by removing the jumper and installing a wire from the voltage supply of the PLL to the circuit that was connected to the jumper. The final modification is to remove the final stage transformer of the VCO. This disables the output of the VCO and gives a perfect connection point for the output of the VFO. Now I prep the VFO for install by wrapping it in some shrink tubing I cut to size and then glue it to form an envelope. I heat the shrink tube on the VFO. Now I add a capacitor to the output coax of the VFO. I needed to use a capacitor because there's DC present on the bus that carries the VCO signal. Once this is done, there are only 4 connections to attach to the VFO. Power positive, the ground, transmit sense, and the VFO output. I make these connections as shown. Next, I mount the display and encoder. The final results are this. The frequency counter shows it is on frequency. Finally, a radio check to confirm it's working. Hello. All right, that's all I need. Thank you.
Sounds good up here. Really good.
10-4, I'll see you on 14.
Pretty cool.
If you enjoyed this content, please like and subscribe. And don't forget to turn on notifications so you see the next video. I am not an expert on CB radios, but I believe this information is accurate.
Okay, so anyway, yeah, we're gonna go off of his sketch to do it because you can get this stuff also from another site called Caesar Sound. So Caesar Sound is another one. And he does the one that they're basically selling on Amazon. Caesar Sound. Julius. Where is it? I don't know. Let's go here again. Dang it. It can't be this soundboard thing. Is it? No. Oh, yeah, it might be. No. Okay, so here's one of the other ones. But this is more directed at ham radio. See what that thing looks like. Nano R3. Okay. Toggle switch, capacitor, the Adafruit SI5351, and the display, software and other services, and what do we got here? Where's the software? So I'm going to actually show it. JCR is Julio Caesar or something. He's got a lot of content too. Looks like some kind of engineer guy. Yeah. Let's see. Copy. Stream. I'm trying to find a specific page to just make things easier. Okay. There we go. I think this is it. Okay. So yeah, he's got a couple different ones. So click on that one. It's basically the same page we were just on, but there's some interesting information here. So I'm going to download this just so I have it. There's the sketch for his, and you can kind of look at the code and all that. But so yeah, we just want to build one of these out of like various parts. So if we go on Amazon, we can look up some of this. Amazon. We go SI 53 51. Okay. There's a bunch of different ones here. All kinds of companies are selling these. Some with these, some without them. I think we probably don't really care about the SMA connectors, but probably want to do it for as cheap as possible. So anyway, there's a few different ones. I think I probably typed something wrong also. Yeah, I did. SI63 SI 53 51. Okay. Okay, so you need to get two of them for $9, one of them for $7, two of them for $14, three of them for $9. They're all different. Some people are like, "Oh, don't buy this one, don't buy that one." I don't know. I imagine they're all probably pretty similar. And we have pages of them. Okay, Arduino. Let's see what we got here. You can buy an R4 for $27. They're using an R3, I think. And these are more like a, I don't know, they're kind of like a Pi. Version V3. It's a Uno. I don't know which one they're using. But the one guy was using a Pico. So I don't know if, here's your R3. It's $16. So okay. So $16 for that. Any of these ones. Whatever one you're going to use. Nano 3.0. You get, I think, a few of them, it looks like. 1, 2, 3. 3 of them for $15. Why is that one at $19? Interesting. It was 16. Here's an R3 for $7.99. Okay, so yeah, should be pretty cheap. I mean, I don't know what one would be the best. I have to do a little more research, but that's kind of the general idea of what we're thinking of doing. I would imagine these ones here would probably be better to use. I'm going to see who used what in their video. These are apparently cost more for some reason. So we just have to figure out which one will be the best. You get $15 for 3. Alright guys, thanks for watching.